In this video, we're going to look at the second half of the Chapter 4 notes. In an experiment, the subjects are often referred to as experimental units. Experimental units is a general term because sometimes the objects are not humans. They could be animals, plants, computer chips, etc. Usually we will say subjects if the experimental units are humans, but this is not a rule, just a usual preference. How can experiments help us avoid confounding? Performing an experiment does not guarantee that confounding is not present. Careful setup and execution of an experiment can prevent the chances of a confounding being present. The best way to prevent confounding is to assign values of the explanatory variable randomly. Definition: in a randomized experiment, the explanatory variable for each subject is assigned randomly before the response variable is measured. The different levels of a single explanatory variable are known as treatments. To set up a randomized experiment, we can randomly divide the subjects into groups and assign a different treatment to each group. Because the subjects are randomly assigned to the treatments, the explanatory variable is not associated with any others. Suppose we have the following people volunteer for a study. In our study, we would like to compare aspirin to Tylenol to see which drug alleviates a headache more quickly. Notice that the two treatments are aspirin and Tylenol. Our first step is to assign each person to one of two groups randomly. We can do this by assigning each person a number from 1 to 12 and using a random number generator to select 6 numbers to place in group 1. Suppose a random number generator tells us that subjects 1, 4, 5, 6, 9, and 10 should be in group 1. This would give us group 1. So group 1 would be assigned Tylenol, whereas group 2 would be assigned aspirin. All the subjects in group 1 will receive Tylenol, and all the subjects in group 2 will receive aspirin. If a randomized experiment yields a significant difference between the two groups with respect to the response variable being studied, we can establish causation from the explanatory to the response variable. If we have a randomized experiment, are we guaranteed that there is no confounding? Just because we randomize an experiment does not mean it is without flaw. One of the goals of a randomized experiment is to treat all the subjects the same in every way except for the actual treatments being compared. Let's look at some examples of things that can go wrong in an experiment. Suppose a drug company developed a new medication to treat severe ADHD in young children. The firm hired a child psychiatrist to test the effectiveness of the drug. He identified a group of children with severe ADHD and randomly assigned them to a drug group or a sugar pill group. Nurse Brock was instructed to administer the drug, while Nurse Ellis was instructed to administer the sugar pill. The two school nurses checked on the children each day and took notes. At the end of the month, the notes were compared. In general, children in the drug group had better attention and behavior compared to children in the sugar pill group. Do you think it's safe to conclude that the drug helps with severe ADHD? Notice that we have a randomized experiment since the children were randomly assigned to drug or placebo group. Even though we have a randomized experiment, there is still an issue with the study. The nurses know if the children receive the drug or the sugar pill. Knowing which drug the children received may influence their perception of the child's behavior, introducing bias into the study. So how can we fix the study? Definition: it's important that the control group be treated as equally as possible. Ideally, the subjects are blind to the treatment to which they are assigned, i.e., they do not know if they are in a treatment group, and if so, which one, or if they are in the control group. In a double-blind study, neither the subjects nor those who interact with them and measure the response variable know which treatment a subject received, which can aid in preventing unintentional bias. Researchers conducted a study on the effectiveness of knee surgery to cure arthritis. Each patient was randomly assigned to have the knee surgically repaired or not. All the patients who had the knee surgically repaired reported feeling less pain. Is there evidence the surgery caused a decrease in the pain? Well, to answer this question, we need to know about what is known as a control. When determining whether a treatment is effective, it's important to have a comparison group known as a control. In terms of the knee surgery example, it's not enough to know that the surgery group improved. We need to compare them to a control. So here we have a randomized experiment, but there's still a problem. And the problem is that there is no control group. The control group in an experiment does not receive the treatment and is used as a benchmark to compare the other groups. In a medication-related study, for example, this group would not receive the active drug ingredient. To be sure that the groups appear identical, they may be given a placebo treatment. This is called the placebo effect and is thought to be caused by psychological reasons. In the knee surgery study, those in the control group received a fake knee surgery, known as sham surgery. The patients were given anesthesia, and the skin around the knee was cut open and stitched back together without doing anything to the knee joint. The patients in the control group had no way of knowing that nothing had been done to the knee to relieve arthritis. Amazingly, all the control patients also reported less pain. In fact, the improvement was indistinguishable between those receiving the real surgery and those receiving the fake surgery. You can read more about this study by following the link on page 15 of the notes. Often people will experience the effect they think they should be experiencing, even if they aren't actually receiving the treatment. This is known as the placebo effect. In an experiment, control groups should be given a placebo and an active treatment as often as possible. Using a placebo is only helpful if the participants do not know whether they're getting the placebo or the active treatment. There's a fascinating podcast about the placebo effect located on the bottom of page 15 of your notes. Take some time and listen to the podcast. Write a one-page summary, including pieces from the podcast, and email it to me before the first exam for 5 bonus points on that first exam. We have discussed randomly selecting a sample from a population, and we have looked at randomly assigning treatments. How do they relate to one another? There are 2 types of randomization we have discussed: randomly selecting a sample and randomly assigning treatments. This diagram illustrates the difference. Ideally, we would like to have both random sample and be able to assign treatments randomly. Fortunately, this is not always possible to do both. If the focus of the study is to use a statistic to estimate a parameter, you need a random sample, but do not need a randomized experiment. If the focus of the study is to establish causation between 2 variables, you need a randomized experiment and can settle for a non-random sample. In section 4.4, we're going to look at other ways to conduct experimental and non-experimental studies. There are many ways to set up an experiment. There's an entire course dedicated to learning about experiments. Watch the video on the top of page 17 to learn about some basic designs. Sometimes simple random samples are not the best or most feasible method of sampling. We're going to look at 2 other sampling methods here. The first is cluster random sampling. Cluster random sampling is when you divide the population into a large number of clusters. Select a simple random sample of the clusters, then use the subjects in those clusters as the sample. Geographical regions such as city blocks or state counties are often used in cluster sampling. This summary comes from your textbook. The other type of sampling we're going to look at is stratified random sampling. Stratified random sampling occurs when you divide the population into separate groups called strata based on some attribute or characteristic about the subjects, and then select a simple random sample from each of the strata. This summary comes from your textbook. So what is the difference between the 2? A stratified sample uses a sample from every stratum. By contrast, a cluster sample uses all members of a random sample of the clusters. In addition, a cluster sample uses predetermined groups to create a single sampling frame, whereas a stratified sample creates multiple sampling frames by strata based on the subject characteristic. Here is a summary of the 3 methods discussed in this chapter. We could also look at the distinction of the 3 using this diagram from your textbook. Read the figure caption on the bottom of page 18 of the notes. Let's look at an example. Suppose I would select 4 students in this room to win a prize, assuming that we were in a room. 1 with last name starting with a vowel, and 3 with a consonant. So let's start by identifying strata. Suppose that we had 100 students in the room, 90 students with the last name starting with a consonant, and 10 with the students with the last name starting with a vowel. These would be our two strata. So what would your individual chance of being selected to win a prize? If your last name starts with a consonant, it would be 90 out of 100. If your last name started with a vowel, it would be 10 out of 100. Notice this is not simple random sampling because not everyone in the room would have the same chance of being selected. In this case, to illustrate cluster sampling, again suppose that I would select 4 students in this room to win a prize. This time I'm going to pair everyone into groups of 2 and randomly select 2 of the groups. So in this case, the clusters will be all of the pairs of 2 students. Notice here, since I'm going to select 2 out of the 50 pairs, you have a 2 in 50 chance of being selected to win the prize. So why is this not simple random sampling? Well, notice that whoever the person is you are paired with, you and that person will always be either in the sample together or outside of the sample. And for this reason, not every possible group of 2 people has the same chance of being in the sample. We could also talk about retrospective and prospective observational studies. Rather than taking a cross-section of the population at some time, such as a sample survey, some studies are backward-looking, retrospective, or forward-looking, prospective. A case control study is a retrospective study in which the subjects who have a response outcome of interest, the cases, and the subjects who have other responsive outcome, the controls, are compared in an explanatory variable. For example, read the example of the retrospective study located on page 181 of your textbook, but also on page 20 of your notes. This study looks at comparing the proportion of smokers for lung cancer patient cases and controls. We'd like to compare the proportion of smokers for lung cancer cases and controls. Doing so, we find the following. Note that these results were shown to be statistically significant, suggesting an association between smoking and lung cancer. We are not at the point yet in the course where we can do these analyses. However, remember that we can never definitively establish cause and effect with an observational study. Read the observational studies and causation section on page 184 of your textbook. There have been experiments and other studies support that smoking is associated with lung cancer. So explain why this particular study had to be observational and not a true experiment. Notice, we talked about this earlier, that in order for this to be a true experiment, we would have to tell some people to smoke and some people not to, which would not be ethical. We'd also look at multi-factor experiments. Categorical explanatory variables in an experiment are often called factors. An experiment in the book, example 7, studied whether taking an antidepressant can help a smoker stop smoking. The factor measured whether a subject used the antidepressant bupropion, yes or no. Now suppose the researcher also wanted to study a second factor, using or not using a nicotine patch. This experiment could now have 4 treatment groups that result from cross-classifying the 2 factors, as shown here. A natural question at this stage in your statistics journey may be, why use both factors at once in an experiment? Why not do one experiment with the antidepressant and one experiment with the patch? As it turns out, we can learn a lot more from 2-factor experiments. For example, maybe the combination of using both could be more effective than using just one alone. Here is a simple design for the experiment to assign subjects to each treatment. Match pair designs and blocking are also mentioned briefly in this chapter. We are not going to do anything with these until later in the term, when we can do analysis with them. Just read over these quickly and note that you will see them again later in the course. This concludes the Chapter 4 notes.